speaker today who is working with one of the companies, TNEI, as a uh, senior power systems consultant, and at the same time is also working with GCU. I will now leave to Sammy to introduce and start the meeting, please.
Thank you very much, Dr. Fildos. I hope you can get me clearly.
Yeah, we can.
Okay, thank you. I think we have now a good number. We can work with that. The
Yeah.
rest maybe will join along the way. Yeah. Once again, good afternoon, everyone, and welcome to today's fitness webinar. My name is Sami Kinga from Glasgow Caledonian University. This marks actually as Dr. Fildos has said, the inaugural webinar in the Fitness Project webinar series. And we're actually delighted to launch it with an exciting project. An exciting topic. Our presenter for today, as you have said, is Dr. Javid Zahid. Dr. Zahid is a power system innovation scientist at TNI Services in Manchester, and in collaboration with the Glasgow Caledonian University through an Innovate UK project under the Knowledge Transfer Partnerships scheme. His work sits at the intersection of industry innovation and academic research. So his focus mostly is on the practical solutions for modern power systems. Today he'll be presenting on advanced network solutions for modern grids and the challenges and innovations. If you have any questions during the presentation, please you can put them or submit them via the chat, and you are welcome to pose these questions anytime during the presentation, and Dr. Zahid will address them towards the end of the presentation. The session will approximately last 45 minutes, followed by 15 minutes of Q&A. Dr. Zahid, thank you for joining us, and the floor is yours. You can begin when you're ready.
Yeah, thank you, Sammy and Frandos, for your brief introduction. So I will be discussing about advanced network solutions for modern grids, challenges and innovation. So I will just briefly introduce myself that I did my BS from UT Lahore, Pakistan, and then I did my master's from China under CSC scholarship. And after that, I did my PhD from Hong Kong under HKPFS fellowship. And I did some postdoc there between Hong Kong Polytechnic University and EPRI USA for a few months. And after that, in March 2024, I joined Glasgow Caledonian University and TNEI as a power system innovation scientist, where I am working on a KTP project currently, which is going to be finished soon, maybe in 2 weeks. And in this presentation, I will be discussing about background motivation about this research, and in which I will be discussing about the advanced power flow methods. I will quickly refresh the memories about basic power flow analysis basics, and then I will dive into the advanced power flow methods and how to speed up those power flow methods that we have developed. And I will be showing some results of those. And after that, I will move forward with the short circuit solver that we developed during the proof of concept of this solver, and how this advanced power flow solver help us to achieve the speed gains with the short circuit solver. And building on that, I will also discuss about how that short circuit solver can comply with grid codes and triple standards, and overview of current limiting strategies and what current limiting strategy we propose to comply with these standards, and the models that we develop for the short circuit analysis. And after explaining this, I will build on that, and I will discuss about how to parameterize the behavior of the short circuit for IBRs. And I will at the end we will have some time for Q&A. So if we discuss about the power flow formulation, so in modern networks we have some complex components that cannot be modeled with the classical nodal analysis methods. For example, we have electronically coupled loads and generators like IBRs, EVs, and we have voltage regulators, which are on-load tap changers. So how to handle those discrete gaps in the load flow calculation and induction machine sleeps. And there are some challenges in the industry that how to model special configuration transformers like rewinding and center tape transformers in the load flow solutions. And also the conventional methods have some limitations when it comes to the ill conditioned network or robustness against those ill conditions, and also how to model these complex components into the formulation while especially considering the nodal based analysis. And if we currently in the industry, mostly the DC solvers are currently used with AC post validation to alleviate the thermal constraints. But this does not allow for optimization of voltage and stability issues. While DC solvers are quick, future analysis requires a fast AC analysis tools. And also the networks mostly are multi-phase and unbalanced. And if we are representing, for example, an IBR asset, so it should be accurately modeled in the unbalanced multi-phase network, because when there is an unbalanced, so it can inject negative sequence currents as well into the network. But it is if it is modeled with the standard PQ model, so it may not behave as IBR unit, and it may, for example, if we are considering the short circuit analysis, it will not give us accurate results. And also, if we want to do the probabilistic power flow, we have to consider the uncertainty modeling, uncertainty of generation and load while we are doing the scenario-based load flow for LV network planning. And if we want to take advantage of the flexibility services on the demand side, like EVs, voltage regulator tabs, and also the soft open points, we have to model them accurately in the power flow calculations. And if I talk about just short circuit behavior of the IBRs, we all know that the synchronous generator, their behavior is linear when there's a short circuit. But for the fault behavior of the IPRs is categorized by the control is the VSC control employed, especially for the FRT strategy, which define the behavior of fault behavior of the IPRs. And for conventional generators, we can find a network. We can compute the network equivalent very easily, which is just a voltage source behind impedance. But for the when we have network which have IBR units, so their behavior is non-linear. So computing a network equivalent for those networks is challenging. And we can parameterize the short circuit behavior, but for that we have to get the large data set using the EMT simulation, which is very time consuming. So we developed a short circuit solver that can compute that data set very efficiently in steady state. And then from that data set, we can parameterize the nonlinear behavior of the IBRs during short circuit. And we also develop a current limiting strategy to comply with IEEE 280/2022 standard, which I will discuss later on in detail, and also how to comply with the grid course when we are developing the FRTs. And at the end, I will discuss about that how can we parameterize the short circuit behavior of the IBRs. So I will start with the power flow solver. So the basics, why we do the power flow. So to find out the voltage at nodes, active and reactive power flow in the lines, and loss in the network. And the purpose of to ensure the network operates within the safe limits under different conditions. And the key applications: network planning, network analysis, network topology optimization, contingency analysis, and congestion management. If we see that any network analysis, we need to do the load flow many times. And the key inputs that we provide for the load flow solver is network data, that is topology, buses and lines, and load data, and also the generation data. And the key output can be a voltage profile, power flows, network losses, tap position of voltage regulators, and sleep of the induction machine, etc. If we see, this is the Goni equation, the basic Goni equation of the load flow, and it can be divided into active and reactive power balance equations. And normally we have three types of buses in a conventional power system, which is like PV, PQ, which is well known, and we have known and unknown for these buses that we have to solve for unknowns. And we use numerical methods like Newton-Raphson, which have variants of fast decoupled and Newton dishonest method. Newton is have quadratic convergence, but it has some problems when there is a ill-conditioned network. And the thing is that how we can improve the convergence of the Newton-Raphson if we use it, if we implement in a good way. And then there's Gauss-Seidel method, but it has some speed limitations as well. So what we do, we linearize the power flow equation using Taylor series expansion. Then we form a Jacobian matrix, and we solve that linearized equation iteratively, and then we update the state variables. For example, we want to find theta and voltage, so we can update until the convergence is achieved. Now I will discuss about in detail that the advanced power flow method that we developed. So basically that is also a nodal analysis based method, but it is modified augmented nodal analysis. Augmented means that it have augmented rows and columns that can be used to model the components which are hard to model in the nodal analysis based method. If I divide this matrix into different parts, so here we can see that these all the components are the linear components. So we can write all the impedance matrix, all the impedances of the network we can model in the Y bus, and then all the ideal voltage sources, transformers, and switches. So these are all linear components. So this is the linear part of that matrices. And in the analysis, I will show later on that how it will help to automate the process while we're using the steady state analysis as well. And below are the nonlinear devices or nonlinear components in the network like PQ loads, PQ generation, voltage regulator. For example, for voltage regulator, there will be three constraints of voltage, current, and the tap position. And then there can be electronically coupled generators or loads, for example, EV operating in V2G or G2V operation. And the good thing about this formulation is it is a modular structure. For example, if we want to add another component into the model, so we don't need to change the product formulation. For example, if you want to add a slip, if you want to add an action machine in the formulation, we don't need to change the product formulation, and it can be added into the formulation without any hassle. And uh, for the state variables, it can be theta, it can be angle of the the magnitude of the voltage, internal EMF of the generator, sleep of the induction machine, tap positions, and current of the IBRs. And the key features is the multi-phase formulation. It's adaptable, robust, and we can juxtap positions of the different components side by side in the formulation. And it is fast, accurate. It can, because the components are modeled with their terminal voltage and current, which are hard to model in the Y bus. So they are more accurate models with the constraints, and they are well. It is the matrix well conditioned. I will explain this later in the result that how it is well conditioned as compared to the classical nodal analysis method. And each component is modeled independently, so they are not dependent on each other. So it can be extended with the different models easily, and it can handle both balanced and unbalanced networks. And to speed up this process of the solver tool for the real-time applications, we do some optimizations. For example, with fast DLU composition of the AX equal to B matrix, of the A matrix in this equation. And we use the AMD, approximate degree, minimum degree, to reduce the fill-ins. And because the formulation is mostly, the matrices are mostly sparse, so we optimize for the sparse matrices to avoid storing and operating on zero elements. That also give us the speed boost. And then we also we are currently working on as well to find a way to innovatively inverse of the Jacobian, because this is the most time consuming part in the low flow solution when we inverse a huge matrix. So we are working on that how can we save time here while inverting the Jacobian. And then tune start from a tune start, a one start from the steady state. It also help us to speed up the process for the low flow solution. So here it's just accuracy validation that we have done for the tap positions in this network. This is the modified IEEE 9 best network. There are two voltage regulators, three voltage regulators, T1, T2, T3, and one of them is the three winding transformer voltage regulator that which we have modeled as well, and we have published on this as well, that how to model a three winding transformer voltage regulator in the load flow formulation. I will share that resource at the end of this presentation. So if we see that there is a set voltage of each regulator, and then there is a control bus, and we compare the result with the IPSA. IPSA is the TNEA flagship software which is used for power system analysis. And there is only one tap position difference at T1, but if you see that with the proposed model, even the voltage are close to the set value. So we tested this with IPSA software, and we find out that accuracy is good of the proposed solver. And then we tested on the IEEE 34 bus test feeder. This is also multi-phase unbalanced network to test that if we model the IBR with the sequence domain, how much it will be accurate as compared to the classical PQ model. So if we see the figure 3, the maximum difference between the voltage magnitude with the proposed model is only 0.05%, and with the classical model is 0.17. And if we see the negative sequence current injection in the unbalanced network with that model, with the proposed, with the classical method, in the magnitude difference is 31, around 31%, and in the angle it is 14.45%. And with the proposed IBR model, the magnitude difference is 0%, and there is a slightly error in the angle which is in the which is very negligible. And to test the boundaries of the solver, we test it on a very large network, which is IEEE 8500 test feeder. So it is, this network is multi-phase unbalanced. It have 4800 buses and 8500 nodes. It have 2000 around 24,000 2400 two winding transformers, voltage regulators. There are four regular voltage regulators of three phase, which makes the 12 units, and it have 500 ECG units like IBRs, electronically coupled generators, four capacitor banks, and it also have some center state transformers and voltage at different voltage levels. So we solved this network in 4 iterations in less than 1 second. And in figure 4, we compare the results of the control nodes of the voltage regulators. The one in the blue is the proposed, and in the yellow is, which is the benchmark, which is published results, and the red one is the set value. So we can see that, and this is the bandwidth of the voltage regulator. So if anything between this, it means that it is acceptable. But we can see that with the proposed method, we are very close to the set value, even with the more accurate results as compared to the benchmarks. And if we consider, if we want to check that how well condition, how robust a method is, we can check it with the condition number of the Jacobian matrix. For example, in AX is to be in this equation. If the A matrix have a large condition number, it means that it is a ill condition A, and it may converge. It may diverge. And for a smaller condition number, the A matrix will be well conditioned. So, for example, there is a three matrices here. A1 is well conditioned, and because its condition number is 1, very low. And if we compare it with 2, so it have a large condition number. It means that it is a ill condition matrix, and the solution might not converge for this type of matrix. And it depends upon the solver. And if we consider the matrix 3 is a singular matrix, so it means that it cannot be converged, or there is multiple solutions for that matrix. And if we see the table 3, we compare the condition number of the proposed Mana formulation with the classical nodal analysis method. We can see that for 9-bus feeder and also for 8500 feeder, the condition number of the proposed method is much lower than as compared to the classical nodal analysis method, which confirms that the proposed method is much more robust as compared to the classical one. Now I will once we have developed that solver, then we utilize that solver to develop the short circuit solver, steady state short circuit solver for the IBRs. And how can we develop a current limiting strategy that can comply with the IEEE 2800? I will explain this standard later on, and also the German grid code. And there was one publication that modified that the current saturation method to comply with the IEEE 2800, but there was some limitations of that strategy, and we enhanced that strategy to strictly comply with this standard. And we also developed the virtual impedance control for the GFM to comply with this standard. And I will discuss about that, what we did to go beyond state of the art, and how we develop the IBR model in the phasor domains, in the sequence domain. And then I will show the proposed methodology of the solver, and I will show some results as well. So on the left side hand, there is a German grid code. So it says that when there is unbalanced fault in the network, the negative sequence reactive current should settle according to the negative sequence voltage variation during and before the fault, according to the K factor. So it is, what does it mean? It means that if there is a fault and there is a difference of the voltage at the terminal voltage of the negative sequence, and the negative sequence current should be the voltage of that multiplied by the K factor. But if we see the IEEE 2800 standard, says that it has some multiple conditions that should follow. For example, the priority shall be given to the reactive component of the current injection unless specified otherwise, and also the incremental positive sequence current for the balanced current for the balance fault. The incremental positive sequence current injection shall not be reduced below the incremental negative sequence current. It means if there is a capacity remaining or over excess, so the both currents are reduced or increased at the same time. And if the current limits reach, equally reduce active and reactive current components. And during the fault ride through mode, the IBR unit shall be capable of to inject the current to its maximum capacity. And the negative sequence current should lead the negative sequence voltage by 90 to 100 degree for the full converter and 90 to 150 degree by type 3 wind turbine generators. And there is also one clause that says that for unbalanced faults, the injection of the negative sequence current shall not depend upon the inverter terminal negative sequence voltage, which is a conflict with the with that German grid code. So while we are defining the current limiting strategy, we should be very careful about that. And when we are developing those IBR models, so we should generalize those models that can be adopted for a grid code which is completing with this standard. And how can we generalize it so it can work for both by adopting very minor modifications into those sequence domain models. So here I just a brief overview of the FRT strategies. In figure 5, we have a GFM control during normal operating conditions. So the outer loop ensures that system level behavior, frequency, and voltage regulation, and the inner loop handles the converter dynamics. And the common configuration for the outer loop includes a droop, a virtual synchronous oscillator, other virtual synchronous machine, other dispatchable virtual oscillator, and the PLL. The droop control, DVOC and VSM are designed to operate during normal and emergency conditions as they provide a GFM functionality inherently by regulating the voltage and magnitude frequency and synchronization under all operating conditions. But PLL, which is generally not used during normal operating conditions and is only activated during the emergency, like during the faults or black start operation. The control strategy implies a hierarchical signal flow where E reference from the outer control loop establishes a VD reference, VD positive reference. Meanwhile, the VQ reference is kept at 0 to maintain the proper alignment with the grid voltage reference frame. The voltage control loop process these voltage reference to generate corresponding current set points ID and IQ for the GFM terminals. These currents reference and then fed into the current control loop. Run control loop of which ultimately produce the voltage modulation signal PWM at the inverter terminal during the fault. And the GFM control tries to maintain this internal voltage vector which can push the required ID and IQ above the inverter's maximum current limit. So to protect the inverter and ensure that it can ride through the fault, additional control loops are integrated in the GFM control system. These additional control loops are activated only during the fault to manage the FRT process as shown in figure 5. So they can be between voltage and current loop, and they can be between outer loop and inner loop depending upon the FRT strategy that we are implementing. The FRT strategy can incorporate additional goals as well beyond the current limiting, such as they can support the grid and voltage frequency stability while complying with the host grid host grid scores FRT requirements. The way a GFM resource behave during the fault is primarily determined by this FRT strategy, and it is active research topic, and there is no universal agreement on best approach. While GFL inverter typically rely on the current saturation method and PLL based synchronization during fault, some GFM schemes adopt similar methods, switching to PLL synchronization when fault condition occur and when there is current exceed the limitation of the set limits. However, GFM inverter also offers unique possibilities for fault management that differ significantly from GFL schemes. The existing literature identified two classification of the FRT strategy. The one is the converter switches from GFM to GFL mode. So it means that it will operate as a current source during the fault, and it will apply the current saturation method like in the GFL to limit the current. And the second one is the converter stays in the GFM mode like in the voltage source, and we can apply the visual impedance control current limiting strategy uh, while maintaining the voltage source behavior. This was just the overview, and we can there's also some hybrid methods that use voltage limiter and voltage impedance here, and then the current saturation method between the voltage and current loop. So there are different kind of strategies available in literature. So this was the paper that I was talking about. There was the authors. You can see the reference at the bottom of this slide. So this is the conventional they developed this. They improved this the current saturation method to comply with the IEEE 2800. The objective was to limit the phase current to the converter's limit 1.1 pu, and to scale up the currents to make sure that at least one phase hits the limit if unused capacity exists. If you see the figure on the left side, you can see there is unused capacity highlighted in yellow, and then they scale up the current in the sequence domain I1 and I2. So they are equally scale up, and they you can see in the figure on the right hand side that it hits the limit on 1.1 pu, and the full capacity of the converter is used. So far, to achieve that in the conventional current limiting saturation method, they add some additional steps. For example, they set the IAB into the in the phase value, and also the limit is set on the phase value rather than in the sequence domain. And also they give the priority of uh, active component of the positive sequence over the negative sequence, and also they set the condition that the active current should be greater than the negative sequence current. But what there was a one problem with this strategy. It works well for near end faults or low impedance fault, but for high for the far end or the high impedance fault, the equation shown in here may not reach the I2 maximum, so it may not strictly align with the standard. And we have modified the strategy by setting the hard limit in the sequence domain. Just I2 max is equal to I max over 2, and then we calculate the I max with this equation. So this ensure that it strictly follow the IEEE 280 standard. And on in figure 7, you can see the proposed methodology for this and how we still use the scaling factor to maximize the converter capacity. So this was the proposed virtual impedance control. You can see the block on the left hand side in the figure 8, and these are the functionalities of these blocks. For example, this block is used to limit the fault current by reducing the voltage reference, and then this block was used to negative sequence current reference generation, and then the voltage drop over the virtual impedance, and the decode voltage drop component, and then finally the sequence current amplitude using the virtual impedance calculation. And the main features of this was it behaves like a voltage source with and without virtual impedance, and the fault current is maximized when virtual impedance is triggered, and the total current is smaller than the if the total current is smaller than Imax, then we don't need to trigger the virtual impedance control. And the positive sequence current is larger than the negative sequence current, which is also a requirement of the standard, and the negative sequence current can lead the negative sequence voltage by 90°, at least 90°. So the main features that the main contributions that we go beyond state of the art. So in current saturation method, there was confusion about reactive current and a decoaxis current, and we have cleared that. We have clarified that relationship, and we consider in our methodology as well. And it may lose power synchronization and the existing method, and it didn't comply strictly with that standard. I will show the result later on. And similarly for the virtual impedance, there was not good distribution between positive and sequence current capacity well, and mostly focused on the balance faults. So we also consider the unbalanced faults as well, and there was a no established phasor domain model. We have also established the phasor domain model of that as well, and we have integrated into this our powerful solver that I discussed earlier. So this was the IBR sequence domain model. So in the positive sequence, we consider the IBR source as a current source, and in for the virtual impedance, we consider it a voltage source as shown in figure C. For the negative sequence, it can be modeled as a negative sequence impedance, or either it can be modeled with the negative sequence current source connected to the network. So and this sequence domain models are integrated into the power flow formation that I showed you earlier. So here is the CIBR, the constraints of that, and the unknown the constraint and the unknown value of the current, and also the other constraint of the voltage and current with the real and imaginary parts of that resource. The good thing of modeling these resource in the sequence domain was that it can be easily adopted to the different grid code and standards. For example, if we want to adopt this negative sequence to follow that German grid code, we know that for German grid code, it should the I2 should be k times V2, which is k is equal to I2 or V2, which is nothing 1 over Z. So it means that if we set the value of negative sequence impedance here is 1 over k, it means it can follow the German grid code easily. And this was the proposed solver of the steady state short circuit solver. For how we'll achieve that? We'll load the network data, we run the pre-fault conditions, we'll linearize the network on those pre-fault conditions, we initialize the IBR short circuit model that I presented previously, and then we apply a fault. After applying a fault, we start an iteration counter, which will call this solver on the left hand side, which is shown in green. So what it will do, it will start to calculate the Z equivalent and Z equivalent and V equivalent with these equations, and it will compute I1. I1 mean a positive sequence current. So then it will check if the positive sequence current is greater than the Imax, it will trigger the virtual impedance. So it will compute the virtual impedance according to that, and it will recalculate the I1 again. And if this current is less than, then virtual impedance will not be triggered, and then we can calculate the current on the LV side of the transformer. And after that, after calculating that, we will compute the I2, and then we check again that if I2 is greater than I2 max, we will set that value equal to I2 max, so it will not exceed that limit. And then after that, we will calculate the reactive current, negative sequence current on the LV side of the transformer as well, minus the filter current, so it will give that LV side current. And after that, we will apply this transformation to get the three-phase currents, and these three-phase currents will be directly incorporated into the B matrix of that formulation, and we don't need to do the power flow, we just need the one steady state iteration, and it will give us that nodal voltage of the network, and from those we can just compute the VF and IF easily. So this was that how we developed that, how we integrated that short circuit models into our load flow solution for the steady state analysis. So here are some results. This is the APRI reduced benchmark. Here we put a fault on a bus 3. So we can say that this is a comparison of the current saturation FRT strategy with the existing method. So we can see that with the proposed method, it hits the limit of 1.1 pu. And also if we see the voltage angle difference, the current angle difference between the negative sequence, it is almost 90 degree. But if we see the existing method, it is less than 90 degrees. So it strictly comply with the IEEE standard. And also if we see the validation of the virtual impedance control, this is for unbalanced fault. So we can see that for unbalanced fault, the voltage difference is 90 degree between the negative sequence current and negative sequence voltage, and also the positive sequence current is greater than the negative sequence current, which is also the case of the current saturation method as well. And for the balanced fault, we can see that there is a zero current injection, because for balanced fault it don't need negative sequence, there will be no negative sequence current injection. So we can say that, we can see that from this also work for balanced faults as well. And this is the results from the full IEEE 120 kV epic benchmark. We apply different faults at different buses, balanced and unbalanced fault, and we compare the speed with the EMTP. With the proposed method, we can see that we achieve almost 3 order of magnitude of the speed gains, and the accuracy that we get is the error that we get for the fault current which compared to the EMT is less than 3%, which is I think a very good trade-off between the speed. So next, I will now we have the we have the power flow solver, and we have the integrated models of those developed short circuit models into the power flow solution, and we can generate that data very quickly as compared to the EMTP simulations. Once we have that data, we can parameterize the nonlinear behavior of the IBRs. So in this, I will be discussing about what was the research problem and how we can develop the voltage dependent network equivalent for those IBRs, and how to represent the system for the different faults, and what are the methodology, what was the methodology that we used, and I will show the results at the end. So for example, consider external grid on the right side, and we have a detailed network, large network on the left side, and there is a point of network equivalent where these both both systems are connected. And for the external grid, it's a conventional sources, so we can just represent with the voltage source behind impedance. But on the left hand side, we have some IBR mod, we have some IBR units that have the non-linear response. So we cannot model them as a voltage source behind impedance. So we modeled it as a current dependent current source, voltage dependent current source, and the current of this voltage source it actually depend upon the voltage at this point, and this voltage is varies when there is a fault impedance varies. So this is the network equivalent we use. This is for positive sequence, and for other faults we can have different representation. For example, this is the system representation into different sequence. For example, positive sequence, negative sequence, we don't represent, we short circuit the source, and in the zero sequence, we don't represent the source impedance as well. So according to these, we can modify that positive sequence voltage dependent network equivalent into according to the fault. And this was the main methodology that we used to gather that data, and then after gathering that data set, how we can parameterize the figure 18. I already explained that how we use a short circuit solver. On the right hand side, I will explaining this. We applied 1,000 different faults on that point that I showed, a point of network equivalent, where we change the fault impedance from 0 to 100